My name is Josh Seeds. I'm the Forest Water Quality Lead for Oregon Department of Environmental Quality. Like I said during introductions, I worked in drinking water protection for quite a few years. And so this is not my first workshop. I'm going to be talking about, the Forest Practices Act as a baseline for water quality protection for drinking water sources and how forest management ties into drinking water provision. So the diagram here is a schematic of a couple different kinds of water filtration plants. So for the water operators in the room, this is going to be really familiar. For everyone else, might not be as familiar. The point of having it here is not that you're gonna, squint up close and read the diagram, but because we tend to think of, especially having such a long history of safe drinking water in this country, multiple generations now, that, it just can happen. Like, just clean drinking water just happens. It's magic. But there's a lot of engineering that goes behind it. And, any engineering is dependent on its processes, and it's also dependent on its inputs. And so any treatment technology, and this varies among treatment technologies, is going to have limits on what kind of raw water it can process, right? So chemical contaminants like, forever chemicals, PFAS, are going to be much harder to remove, but even pretty basic stuff like, sediment and organic matter that need to be removed from drinking water are going to have limits on what can happen with raw water. And regardless of that source water quality, any public water system is responsible for meeting the maximum contaminant limits set in the Safe Drinking Water Act. So if it's very, very high quality water that hardly needs treatment at all, then that's easy to treat and they're going to meet those limits easily. If it's water that has a lot of contaminants or a lot of sediment in it, it's going to be very challenging or possibly impossible to treat, but that water system is still legally responsible to meet those maximum contaminant limits. Again, a couple tables here. The top table is from a study on water quality pre and post wildfire. So this is a severe wildfire and how it's affecting turbidity and organic carbon. So if you've heard of disinfection byproducts, that's generally from organic carbon reacting with chlorine or amines or other treatment chemicals for disinfection. And so what it's showing is that pre-fire and for post-fire reference sites that weren't burned, turbidity average was pretty low, 3.6, 4.4. And then in post-fire areas for routine monitoring, it shot up to 35 turbidity units. And then during post-fire rainstorm, 321 was the mean turbidity. So it really shot up. And then that table below that is what's the turbidity range that different systems can handle. So like a direct filtration system needs less than 15, pressure sand needs less than 5. And so for a lot of smaller water systems, especially, really less than 5 or less than 10 is going to be the treatment limit. And that's not really visible in a vial or cup of water to the naked eye. But that even that small amount of fine sediment at, say, 10 NTUs is going to add up pretty quickly when you're moving millions of gallons of water through that filtration system. So for source water quality, can be pretty low as far as what the contaminant limits are, in this case, turbidity, that it can handle. Like I said, they're responsible for putting out safe water that meets limits, no matter what's going on with the source water itself. All right, so back to a diagram of system design. In this case, it's from similar wildfire papers about design stuff to deal with changing water quality due to disturbance like severe wildfire. So, the question becomes, for a water system, do they want to upgrade treatment or do they want to protect their drinking water source? or maybe they'll have to do both. Upgrading treatment is very, very expensive. It's often cost prohibitive. And of course, there's maintenance and operations costs that go along with increasing the capacity or the number of steps in the treatment train that is in a drinking water system. So if possible, it's better to take a different approach and protect the source water to minimize that. So pretty good history of this: New York City, Boston, Portland, Oregon, and Seattle, Washington are some big cities that all have managed to use source water protection as a means to either delay or avoid having to upgrade treatment in very expensive fashion. So in drinking water protection, we talk about this as the multiple barrier approach, where we want as many barriers as possible between people drinking water and potential contaminant sources. And so the ecosystem that the water is being derived from is that first barrier to contamination, and often the most cost effective. Treatment processes themselves, maintenance and testing of finished water quality form additional barriers. So in general, the strategy for drinking water protection, for protecting sources of drinking water, it's going to be to identify potential contaminant sources and risks. So, focus on the word potential. It's just because there's a possible source doesn't mean that it's a definite contaminant source, but we want to know what's the potential out there, where do we have risks, so we can make intelligent decisions about managing those risks. And then where we see those, we want to use risk reduction and risk avoidance strategies to prevent contamination in the first place whenever we can. So for watershed management, that's going to be using practices ideally that are low risk or no risk, if there's any such thing in the world, to minimize those treatment costs. And ecological processes and ecological resiliency will not only, reduce risk from potential contaminant sources, but also reduce the impact of natural or human disturbances, because the ecosystem can absorb some or all of that impact. And over the long term, that should save money and resources while providing safe drinking water to ratepayers. So we're in the coastal area, lots of forest land, mostly forest land. And that's fortunate if you want clean water, because forest land, whether it's public or private, provides generally the highest quality water for drinking water. Forests do quite a lot of work on their own. They slow down water and store it. In the coastal zone, they can capture fog. The trees will precipitate fog and it drifts into the soil. But also during the winter, when we have high volumes of rainfall, the forest canopies and those deep forest soils will slow that water down, prevent it from running off right away, and store it where it'll still be percolating down well into the summer months, and providing water then. And so those soils, the vegetation, wetlands are excellent. They all moderate water movement. They slow it down when there's a lot of it, and they release it when there's not as much. And then the tree canopy and different vegetation layers, shrubs and ground plants, stabilize the soil and build it over time, increasing that water storage and filtration capacity. So forests are really excellent first filter for drinking water. So getting into management, the Forest Practices Act and the rules under it are the baseline for water quality protection for drinking water. And as Rebecca detailed, those rules for water protection in particular were updated substantially by the Private Forest Accord. I want to emphasize this is a really big uplift in terms of moving the baseline for protection during operations on private forests and any non-federal forests in the state of Oregon. These rules do have a threatened and endangered species focus, amphibians and salmonids. So those are the covered species, and those covered species evolved with natural disturbances. And in fact, natural disturbances like landslides contribute to habitat building processes. So those species really evolved in a situation where, here and there on the landscape with some frequency, you get natural disturbances that might cause a short-term impact to water quality or to physical habitat, but then over time builds that up. So a landslide loaded up with trees is going to be pretty devastating to any salmon eggs in the area where it hits. But 2, 3, 10 years down the road, that's going to be really amazing habitat with a lot of downed wood and a lot of gravel. So drinking water, fish, wildlife, those are all beneficial uses that are addressed in the Forest Practices Act rules and the best management practices within those rules. And they're all going to be benefiting from these changes, recent changes to the private from the Private Forest Accord to the Forest Practices Act. And the fish protections that Rebecca detailed went into effect last July. All the rest of them went into effect January 1st of this year. So this is very new. We're just starting to see what these rules are doing on the ground. So I'm going to make a quick diversion to talk about climate change. And, this is something we're definitely seeing. Oregon just had a record fire season, largely east of the Cascades, but right in the area where you all are in the mid-coast. 4 years ago, we had the Echo Mountain fire, which impacted Water District's drinking water source area, and it was a very intense fire in an area we don't usually think of as having intense fires in the wet coastal zone. So we're getting higher temperatures and drier summers. The summers are having less precipitation, and the dry season is often lasting longer. And so that's going to result in lower stream flows during summer and early autumn. And then on the other side, wetter winters and with more intense storms, longer, more intense rainfall, that's going to increase erosion and flood risk. So we're kind of getting it, both in the dry season and the wet season. And those changes that we're seeing just based on climate and weather can potentially interact with management effects on stream temperature or on erosion or landslide risks. So that's something we want to consider during management is that we're not managing for how things used to work 40 years ago. We're managing with sort of a more intense climate system. And so we want to be careful of how vulnerabilities that might be created through management are going to interact with vulnerabilities being created by climate change. And so for a couple examples of that, the diagram here is from a paper looking, a Forest Service paper looking at how tree species ranges are shifting already and how are likely to continue shifting. So this particular tree species is for Douglas fir. So the more kind of yellow-green colors are where they're likely to persist or move to as time goes on, and then the more purple colors are where they're less likely to persist. So this is going to be happening a lot, where a lot of tree species are moving northward or moving upward on the landscape. And pests and pathogens are shifting as well. For example, bark beetles that previously could only get one generation in a growing season or with longer, warmer growing season. They can get in 2 generations. So the impacts from pests and pathogens can be higher as well. And as I mentioned, wildfires are getting more frequent and more severe. And so with all that, we want to plan ahead for shifting climate patterns and shifting species ranges. A lot can happen over a 50-year timeline. So during planting and other management decisions, it's important to plan for climate change, plan for species change. So of course, in a drinking water context, we think about infrastructure, the treatment plant itself, the intake structure, the distribution system, and it's understood that needs maintenance. And it's going to require money and effort over time to maintain that gray infrastructure. But forests are natural infrastructure, and with healthy forests that are resilient to disturbance being an important part of the multiple barrier approach, we also want to remember those forests require maintenance the same as built infrastructure does. And the foresters and industry folks in the room are all too aware of this. And so for water systems that are thinking about purchasing parts of their source area or participating in management within their source area, you want to understand that with the land comes costs like road maintenance. There's going to be tree planting and care, possibly tree removal and thinning, firefighting needs, property taxes. Those all cost time and money. And so just like with built infrastructure, forests need maintenance and to be maintained as functional infrastructure. You do get to let them just grow and do their thing quite a bit, but they don't just grow on their own, and they do need some tending, especially things like roads. So to get into drinking water protection, risk management in the forest landscape. So in contrast to the species like amphibians and salmonids that have some resistance, and even have evolved in an environment of some disturbance, and that is a habitat building block, like these trees falling in here on this steep slope next to a creek. Drinking water provisions very, very sensitive to sediment and organic matter in water. You can have a salmon run get knocked out of a creek for a few years if there's neighboring places they can recolonize from once the habitat sets up after the disturbance. Can't really do that with drinking water provision. Most systems have one, maybe two sources, and the need for water is pretty constant. So other than a few days or a week of storage, can't really just go without water for very long. And in terms of the turbidity levels, for example, or the organic matter levels that can be handled in drinking water treatment, those are very low compared to what matters for aquatic and riparian species. And so that needs to be kept in mind when managing in drinking water source areas. And that's why if the landowner and the water system are different people, collaboration is really necessary and needed. I think it's also important to differentiate between definite and potential impacts. And that is very dependent on the particular conditions of the site, on the vagaries of weather and climate, as well as any actions that people are taking on the ground. And so there's a big gray area between, if you do X, you will definitely have an impact, and if you do Y, there's very little chance of an impact. There's a lot of gray area in between those two things. There's no fine lines here. That's going to, again, depend on site conditions, and what the management goals are, and so on and so forth. So that said, the Forest Practices Act is a really excellent baseline, and like I said, it's an even better baseline than it was just a couple years ago, thanks to the efforts of the timber industry and the conservation groups and the leadership of our previous governor. But one thing, that water systems can do and landowners can do is to look for opportunities, using the Forest Practices Act as a baseline, to reduce risk even further. And so that's in riparian areas that might be, be very careful to avoid or cover any bare ground, to leave fallen trees along the slope contour and or in stream to capture any sediment that might be mobilized, let that early successional native vegetation do its thing and cover and build soil. Or in some cases, even maybe leave wider buffers, which is a practice I've seen some landowners implement. So an example there might be those 20-foot no-cut areas on the type D streams. Those can be prone to wind throw, especially with the winds coming off the ocean. So going a little wider there can reduce wind throw or keep the root wads and soil disturbance away from the near stream area. Steep slopes, for example, the way that the steep slope protections are designed, it gets a small subset of the steep slopes get no harvest protections, and it's got a tier setup that Rebecca didn't have time to describe, but basically what it does is it finds those steep slopes that are most likely to fail and deliver directly to fish streams. So it's really getting the worst of the worst, and making sure that we're not increasing the failure probability, and that if they do fail, they're delivering large wood into the streams, which helps trap sediment and create habitat. But there might be cases where for a drinking water system, we might want to extend partial or no harvest protections to additional designated sediment source areas beyond those that are required to be covered, especially if they're near the intake. And also those requirements don't extend to small forest landowners. So that might be an area where a water system would want to work with small forest landowners to help them keep trees on those designated sediment source areas to reduce failure probability and to help filter any soil introduced if there is a failure. And then, again, our friend early successional vegetation does a great job of stabilizing soil and preventing raindrop impacts, for example. Water quantity, it's one of the most studied things about forest harvest is that removing a lot of trees causes changes in the flow. So shortly after harvest, we'll see increases in peak flows. And then as we get a young stand of thirsty trees, low flows can decrease, which is an issue in the summer. And so, ways to handle that would be to limit the extent of recently harvested stands. On the low flow side, we might reduce planting density, and then growing multi-age or multi-species stands will, also help moderate flow changes due to forest management. On roads, there's not a lot to do, to be honest. The new road rules are so robust and have so many checks in them, and large forest landowners really have to do a very thorough analysis. So there's, I think that's actually really solid, but small landowners, are going to always have trouble with funding repair projects. So I think that's a real opportunity for water systems to work with small landowners and help them fund road repairs that will then benefit the water system. So that could really benefit both the small landowner and the public water system. Herbicide application, likewise, we do sometimes see very low levels of herbicide move after application, typically far, far below maximum contaminant limits. But one of the things that tends to happen is rain shortly after application, especially if it's a surprise rain. So, there's alternate approaches to control competing vegetation, but when herbicides are being used, looking far out on the forecast and avoiding application when there's going to be rain, so it has time to really absorb into the target plants is also very helpful. So kind of my, pie in the sky, if we really want to minimize risks to drinking water to the maximum extent possible, we'd retain required leaf trees or additional leaf trees around sensitive sites. So something I've seen company foresters do is identify, wet soils or seeps and springs by the plant communities there, and then just put extra trees around them. If we've got buffers that might be prone to wind throw or spots that are particularly steep, leaving trees could be beneficial and reduce risk. Again, focusing on not saying, well, this is a definite impact if we don't do this, but just saying, well, there's a risk here and we can reduce it more because of the importance of drinking water. Limiting size and extent of canopy removal. The picture here is another option that helps with flows, but also helps with surface erosion. The picture here is from Astoria's drinking water source area, which they own and manage. So this was an opening to create some structure and to thin out a highly dense stand that was struggling, opening up a few acres at a time sort of approach. And like with anything that's engineered, with a forest that's used for drinking water source area, redundancy is good. We want, if we can, multiple canopy layers, overstory, understory, ground plants, and multiple ages and species of trees, again, referring back to changing climate patterns and changing species ranges and pests and pathogens. If we have a lot of ages and species of trees, then if one age class or one species is affected by a pathogen or a pest or water stress or so on, we have other tree species that can fill in and take over and keep the system moving and healthy. But we also have to be realistic about what it is we're asking for if the landowner is someone other than the water system. Reducing risk is often means we're asking to have more trees left behind, and to avoid disturbance around sensitive features. And so leaving trees, from a business perspective, means leaving revenue. And so there's a trade-off there, that we should be aware of. And that might mean that water system might need to pay for ecosystem services. And I think Daniel Weir from Sustainable Northwest will have some good examples of this kind of working together, with the landowner reducing risk beyond the FPA, and the water system helping them cover those costs that they're incurring by doing that. So yeah, and like avoiding sensitive features might also just make the process of extracting trees from the landscape more expensive, more challenging yarding of felled trees, for example. So it's really key to have collaboration and good communication here, and to think about how additional risk reduction might have a cost associated with it, and how those costs are going to be shared. And then, of course, site variability and weather fluctuations, like I said, it means that the effectiveness of practices has uncertainty. A practice that is a slam dunk in one place, or during a mellower year weather-wise, might not be as effective in a year of more intense weather, or in a place with different vulnerabilities, like, say, very steep slopes or sandstone geology. And so there's a lot of options between definite impact and that situation of minimal risk. And again, I'd reiterate, there is no zero risk situation. These are forests or natural systems, and they're even unmanaged. They are prone to disturbance, and that's part of the ecosystem and part of the landscape in which we're getting our drinking water. Finally, like with a lot of things, when you're investing care and money wisely, the costs are mostly incurred in the short term. Whether it's restoration, payment for ecosystem services, tree planting, tree thinning, et cetera. And the benefits may not accrue until much, much later. So especially if you've got a system that has been through a disturbance recently and you do a bunch of restoration work, it's probably going to be a few years before you really start to see those restoration benefits. And certainly if you're planting trees with the intention of harvesting some of them, it's going to be a while before you get those benefits. But overall, we just want to manage watersheds to prevent immediate impacts, reduce the overall risk, identify hazards, and then see, are those hazards going to actually have a chance to impact the water system? And if so, how do we keep those hazards out of play as much as possible? And then overall have a resilient ecosystem with layers of redundancy. And that's it. Thank you.